And while dealing with bending stress, we took a beam in which the bending moment was constant, like this. Okay, for example, this is the beam what we have taken. So in this portion, you don't come across any shear force being subjected to the beam. You can see here the shear force diagram, the shearing forces are zero, whereas the bending moment is constant here. Okay, now in case if the beam is subjected to a varying or non-uniform bending moment, then you will also encounter shearing stresses in addition to bending stresses in the beams. So this is how a non-uniform bending will occur. Now in this case, we will take a cantilever beam, a case of a cantilever beam subjected to a concentrated load at the free end. This is the concentrated load what is applied at the free end of this cantilever beam of span L here. Now if you look at the bending moment variation, it is zero at its free end and it will increase towards the fixed end with a maximum value of P into L over here at its free end, okay, or at its fixed end, that is P into this distance L, that will be the bending moment at its fixed end. So this is varying, the bending moment is not constant here, it is varying here. Now if you take any small portion within the span of the beam, okay, of this dx element, you'll find that the bending moment on left side of the portion is m, whereas on right side it will increase like m plus dm. Okay, so under such a situation, what happens actually in the cross section here? Now this is the cross section what has been taken here. So the bending stress variation you can see. Okay, it can be represented like this also. What we are taking the diagram earlier in this way also. Both are same. Only thing is nature of stresses are different. Okay, on one side it will be tension, on the other side it will be compression. Okay, so when you have such a non-uniform bending in beams, okay, so what happens actually? Now this is the cross section of this beam. Okay, and what you have in this cross section, this element has been enlarged over here. So on top side, sigma b1 are the stresses, okay, on this left face, and on the right face the stresses are sigma b2. Okay, let us take the section above the neutral axis. So on the top face, sigma b1 is the stresses, maximum stress on the left face, and on the right face, sigma b2 is the maximum stress. Okay, so this part are kept it over here, the same has been taken out. So sigma b1 maximum stress on the left face, sigma b2 maximum stress on the right face. So since there are stresses acting on these faces, they will also be subjected to forces here. Okay, say F1 and F2 are the forces which are acting on the two face. Right, left face, the force is F1, which we can obtain by multiplying this sigma B1 with this area. Okay, so we can find that force F1. Similarly, F2 is the force which is acting on the right face here, right? So clearly what you can notice here is F2 is greater than F1 here, because there are bending moments which are not same. It is not constant, m and m plus dm, two bending moments. Okay, on left face m, on right face m plus dm, the bending moment has increased. So evidently what happens here, the stresses on left and right face, they will not be same. Okay, the stress which is developed, the bending stress which is developed on the right face will be more than the bending stresses which are there on the left face of the section. So from that, the forces also will be differing. So I can say F2 is more than F1 from that. Okay, now let us say net force. What is the net force on this section? If I call it as Ft, it will be equal to F2 minus F1 here. Okay, so F2 minus F1 is this net force which is acting on the section, on this particular portion of the beam which is above the neutral axis over here. In this portion, the net force is F2 minus F1, which will be FT, which we'll call it as FT. Okay. Now, if we just look at this FT, this is an unbalanced force here. Okay. So a beam cannot be under equilibrium under an unbalanced force. There has to be some balancing force here. Okay. If this beam is under static equilibrium, there should be a force which will balance this FT. This FT is acting in horizontal direction on a longitudinal plane here. Okay, in this longitudinal direction. So there will be a force which is acting on this bottom face. Okay, F. So this is the force which will balance this Ft. So for equilibrium, what happens? For equilibrium of this section, that is A dash, B dash, and B. This Ft, okay, has to be equal to F. F is the balancing force. And F, it is acting on this longitudinal plane. Please keep in mind, it is a force acting on this particular longitudinal plane here within the beam on this plane. So F will be acting on this plane here, okay, here within the beam. So that is the force which will be acting. Now this tells us that there is some stresses which are developed on the longitudinal plane also. Okay, these are the longitudinal shearing stresses here. So F comes due to that longitudinal shearing stresses which are developed on the longitudinal plane of the beam. Okay, so that is what we can conclude from this. Now what we want here is we want to arrive at an expression which gives me the stresses which are developed on this longitudinal plane. On this plane, I want to know what are the stresses developed here on this longitudinal plane. There will be shearing stresses tau. Okay, I want the expression for that too, the shearing stresses on this longitudinal plane. Okay, so we are going to arrive at that particular equation. I hope this part is clear. What we actually concluded in this part is there are shearing stresses which are acting on this longitudinal plane in case of non-uniform bending. Okay, in case if bending is uniform, if it is constant, say instead of this load P, a couple is applied over here, then what happens in that case? There will not be any variation in the bending moment. M and to the left and right, bending moments will be M itself. It will not increase when you move from left face to right face. So there is no question of unbalanced force coming in picture in that case. So it is not subjected to any shearing forces. A beam carrying uniform movement will not be subjected to any shearing forces or shearing stresses. It will experience only bending stresses. Okay. Now, if at all, if the beam is subjected to a non-uniform bending, this is a non-uniform bending, what you see here. Okay. Bending moment is varying linearly. Okay. I've taken a point load. So it is varying linearly. In case if it is a UDL, it will vary parabolically. UVL, it will vary cubically. Okay. So these are the cases of non-uniform bending, wherein bending moment is not constant. It is increasing from one point to another point like this, what you see here. Okay. So in this cantilever beam, bending moment is zero at the free end and maximum at the fixed end. So it is changing along the span of the beam. It is increasing. Now what we did here, we have taken a small portion of beam of length dx, okay, and that we have separated out here, right? Now on this section, what are the bending stresses? If we take the left face, there will be bending stresses developed due to this M, which is acting on the left face. The bending moment M is acting on the left face. So due to this moment, which is acting on the left face, okay, this is the moment which is acting on this left face. These are the stresses developed here. Sigma B1 is the maximum stress on the top face, top side of the beam. Similarly, on the right side, what you have, bending moment is M plus dm. Okay, so here the maximum stress is sigma b2. So these are the stresses, bending stresses which are acting on our cross section. Okay, now in this what I have taken is I've taken this top part of this section, this a dash b dash b. So that is shown here. This one, this same part, I have taken it and I have shown it over here. So let us look into this here. So bending stresses, maximum bending stress, sigma B1 on left face, and on right face it is sigma B2. Okay. So what happens under this situation? There will be two forces which will be acting, F1 and F2. On the left face, the force which is acting is F1. This is a horizontal force acting along the length of the beam here. So because of the bending stress on the left face, F1 is the force, and on the right face, F2 is the force. Now, since sigma B2 is more than sigma B1, okay, in magnitude or in intensity, what we get is F2 is greater than F1. So the force F2 on the right face of the beam, this section, is more than F1, okay, which is the force on the left face of the section. Now, what is the net force? If you find the difference between these two, that will tell you what is the net force which is acting on this section. So let us call that net force as Ft. So Ft will be F2 minus F1. Okay. So this is the net force which is there on the beam, Ft, which will be equal to F2 minus F1. Now, because this is a net force which is acting here, beam cannot be under equilibrium only under the action of this force. There should be a balancing force which will be coming due to the shearing stresses which are acting on this longitudinal plane. Okay, this is our longitudinal plane. This is my longitudinal plane, and on this longitudinal plane we will be having shearing stresses tau, which will be acting over here. Okay, this is the transverse plane. What you have here, this is our transverse plane, cross section of the beam. This is that transverse plane. Now, what I am interested here, I am interested in finding this shearing stresses on the longitudinal plane of the beam. Okay, so we are going to deal with that derivation of the equation for shearing stresses in that beam when it is subjected to non-uniform bending. Okay, now this is what I wanted to make clear, how that longitudinal stresses will come in picture in case of non-uniform bending here. Okay, that is the first point what we have seen in this. Now further what we'll do, we'll move to the expression to obtain an expression for these shearing stresses on a longitudinal plane. Now let us come here and we'll take a beam which is subjected to non-uniform bending. This is the section of the beam of width dx, okay, and this beam is let us say it is a rectangular in cross section. So this is the cross section of the beam. So this is actually your beam. This is width of the beam B, and this is the depth of the beam D. Okay, now you are looking at a section taken somewhere over here on its length. It is subjected to a movement. So this is dx. Okay, this may be a simply supported beam, cantilever beam, whatever it may be. But thing is, it is subjected to a non-uniform bending here. Okay, non-uniform bending. So what is happening here? On this face, movement is m on the left face, whereas on the right face, on this face, the movement is m plus dm. So this particular part of the beam has been separated out from here and it has been shown over here. Okay, so this is that section what I have taken here. So here the width is not visible, but this is the section along the length. Now what happens because of these two movements, there will be stresses. This is the distribution of stresses on the beam. So here what you have, sigma, let me call this as sigma BL, stress on the left face, and sigma BR, stress on the right face of the beam. Okay, so sigma BL and sigma BR, okay, they are the stresses which are acting. Now to obtain the expression, I'm just taking section somewhere over here, okay, of depth dy. Okay, this is the entire cross section of the beam what you are seeing here. Okay, so in this entire cross section, to determine what is the stress, just okay. So I showed you that beam, how this section appears in that beam. From that, what I will do now is I'll consider a small element in this cross section of depth dy here. Okay, this is the depth of the cross section dy, and it is at a distance y from our neutral axis. Okay, so on that section, this is my section what I'll be considering there. So cross section of the beam, the movement on the two faces, and further in this cross section, this is our entire cross section. I'll be dealing only with this small elemental part of depth dy. Okay, so here you can see this portion of depth dy, this element which is having a depth dy, it has been shown here. Okay, this is actually that small portion of the beam which is taken out from the entire beam cross section. Okay, now here what we have, these are the stresses on left and right face of the beam. Let us say this is sigma bl, okay, and sigma br. These are the stresses which are acting on left and right side face of this section. Okay, so I can now write what is the expression for sigma bl as well as sigma br. These are the bending stresses. So the bending stresses acting on a small element of depth dy. I am interested in knowing what are the bending stresses acting on the small element of depth dy. Okay, so here we'll take it as sigma bl and sigma br on left and right face. Okay, so on this small element, on left face, the stress is sigma br. On right face, it is sigma br. Okay, what is this sigma bl equal to now? So from flexural formula, so what I have from flexural formula, the bending stress sigma is given by m by I into y here. Okay, so this is the flexural formula what I have. Now if this formula is applied for calculating sigma bl and sigma br, that is the stress on left and right side of our element. If I apply this formula, what it tells me, so I'll be having sigma br here as m by I into y, whereas sigma br will be, so therefore what I can write, sigma bl L will be equal to simply M by I, okay, into Y. M is the moment acting on left face, this one, okay. I is the moment of inertia of this section, entire beam cross section. And at what distance I want to know the stresses? At a distance Y from the neutral axis. This is the layer of neutral axis. So our element, what we are taken, it is at a distance Y from this neutral axis. Okay. So at this point, I want to know what is the stress. One on left side face, other on the right side face. So on left side face, it will be simply M by I into Y. On right side face, what happens? Sigma BR. What is the moment acting on the right side face? It is M plus dm. So here I can write it as bending moment will be M plus dm here, divided by moment of inertia of the beam cross section into what is the distance from the neutral axis? Same, y distance. Both faces are at a distance y. Left face as well as the right face, they are at a distance y from the neutral axis. So these are the stresses. Okay. Now coming to the forces. What about the forces? FL and FR, what are shown in this figure here? These are the these are the forces which are acting on left and right face here. Okay, on left and right face. Just like what I said in the first part, F1 and F2, here the forces are FL and FR. Left side face FL, right side face FR. Now how to determine these forces? Okay, so forces acting on the two faces, left face and right face, due to bending stresses. So what I have on the left face, it is FL. Now that will be equal to what? Sigma BL stress into the area on which it is acting. What is the area? It will be the area of this face, this area, what you see here. What is this area equal to? This is the width of the beam from here till here. Okay, this is the width of the beam, and this is the depth dy. So sigma BL multiplied by B into dy. This is my area of that face. Why I have taken a small element dy? So that this variation in the bending stress is neglected, so that we can neglect here. For that purpose, we are considering a small depth dy. So this stress sigma PL, which is acting on the left face, okay. So in this here you can see sigma PL is the stress on the left face. So that stress multiplied by this area of the cross section B into dy. That will tell you what is the force on the left face FL. Okay. Similarly, force on the right face can also be applied. Here what I have sigma BL, it is M by I into Y into B into dy. So this is the force which is acting on the left face. Okay. And similarly on right face, this is on left face. So on right face, we have FR. The force acting is FR on the right face. So it will be the stress on the right face sigma BR multiplied by the same area B into dy. Okay, or this will come out to be the stress on the right face will be in terms of the moment M plus dm divided by I into y. This is equal to sigma BR multiplied by B into dy here. Okay, so this is the stress on the right face. Now what is the net force? If these are the two stresses, what is the net force? So what we have is, here is F, the force on right face, Fr will be more than FL, because moment acting on right face is more than moment acting on left face. M is the moment on left face, whereas M plus dm is the moment on the right face. Therefore, net force acting on the element will be equal to, let us say it is ft, it will be equal to fr minus fl over here. So that will be the net force what we'll be having on that section. Okay, so in this you can see this is the net force dft. It is dft actually, because the section what we are considered is a very small elemental section here. So that will be the net force. So this is dft. Okay, therefore what I can write, I have dft equal to what, m plus dm divided by I into y, okay, into b into y into dy. Okay, this is the force minus m by I into y into b into y into dy over here. So that is the difference, fr minus fl. So finally, if you subtract these terms, then you will be left with dm, okay, upon I, m and m will be gone totally, into b into y into dy here. Okay, so if you integrate it, on integrating, between what, between the limits yb and yt, because we have taken a small element here and we have determined what is the force acting on this small element. But actually what we required was in this portion of the beam, that is a dash, b dash and b, in this portion. If I want to know what is the force, net force acting in this portion of the beam, I have to integrate that between yb and yt. What expression we have got here? Yb, bottom fiber of the this section, and yt is the top edge of this section. Okay, so if I integrate this between yb and yt, I'll be able to find what is the net force ft here. So that will be equal to this dm upon I, okay, or integration between yb to yt into b into y into dy here. Okay, so that will be the integration term here. Further, if I take that, ft shall be written as dm by I into integration yb to yt into b, dm by I, that will be a constant term. So what I have, what was there previous term, so it is b into y into dy. So this comes out to be, okay, within the brackets I have b into y into dy. Okay, but in this case b into dy is the area of that elemental portion. I can call it as dA. So further this comes out to be dm by I into integration yb to yt into y into dA. That is what I can write here. B into dy will be the area of that small element. So y into dA. And this integration y into dA is nothing but the moment of the area, entire area about the neutral axis. So this will be a into y bar. Okay, moment of the area. So this further can be classified. This is from the centroidal distances what we have. Integration y into dA, okay, divided by a will be y bar. So y bar, what you have, integration y into dA upon the total area A, or what I have is A into y bar. This is how it comes, y into dA. Okay, so this is what I have substituted here. Okay, so what finally I'll get, Ft will be equal to dm by I, okay, into what is this term, A into y bar here. Okay, dm by I into A into y bar. So what I got here, the net force which is acting on that section, A dash, B dash. So this is what it is. Ft is the net force acting on A dash, B dash. This part, okay, this portion. Where is that? A dash, B dash, and B. Okay, in this part, this is the net force Ft, what is acting. Okay, now this has to be balanced. So for equilibrium, what we have? For equilibrium, Ft, it is balanced by the force developed due to shearing stresses on the longitudinal plane. Let us say it is F. Okay, shearing stresses on the longitudinal plane. So therefore, what should happen? Ft has to be equal to F. Okay, so if this is our beam cross section, what we have, so on this longitudinal plane, the shearing stresses will be there, tau. Okay, what will be the shearing force? It will be this shearing stress multiplied by the area on which it is acting. So it will be over here. What I have taken is this part of the beam. So this is dx, okay, and this is b. This width is b. So in this portion dx, or in this part, okay, whatever the shearing stresses are there on that section, tau multiplied by this shaded area, which will be equal to dx into this b. B is this width of the beam. So this shaded area will be dx into b. So what I'll get, F will be equal to tau, shearing stresses which are there on this longitudinal plane, multiplied by b into dx here. Okay, or what I have, Ft will is equal to dm by I into A into y bar. Okay, so this should be equal to tau into B into dx. Further, what I require actually, what is the expression for this shearing stress? Okay, so that shall be equal to what, dm by I into 1 upon B into dx, okay, into A into y bar. Further, if I rearrange this, dm by dx, okay, into A into y bar divided by I into B. I can write it in this form. But what I have is, wait. So what is dm by dx? We have seen in the earlier module the variation dm upon dx is nothing but the shear force. Okay, so this we have made it in the previous module. Dm by dx, okay, is nothing but shear force at that section. So therefore, what I can write expression for tau as F into A into y bar divided by I into B. So what we got here is the expression for the shearing stress in a beam. Okay, expression for shearing stress in a beam on a longitudinal plane. Okay, so whenever you have beam subjected to non-uniform bending, you will encounter these shearing stresses on the longitudinal planes. And what is the expression for this? Tau, okay, it is F-A-Y bar upon I into B. F is the shear force at that particular section where you want to calculate the shearing stress on the longitudinal plane. A, cross-sectional area of the element above the neutral axis. Y bar, centroidal distance of this area A. I, moment of inertia of the beam. B is the width of the beam. Okay, so suppose if you have a rectangle section, say if I take a section, rectangular section, this is the neutral axis, width is B, depth is D here. So this is D by 2, centroidal distance of the position of neutral axis. Okay, now I want to know what is the shearing stress somewhere here at this section XX. Let us say this is at a distance Y from the neutral axis. Okay, so this is the area A, what you need to consider. Okay, this is A. What is Y bar? If this is the centroid of this area, this is Y bar, distance of centroid of this area from the neutral axis, that it is Y bar. What is I? I will be BD cube by 12. Okay, shear force. F is the shearing force which is acting on this section over here. Okay, so in any beam we can calculate shear force. What is the shear force at any section can be calculated. Okay, so if you want to know what is the shearing stress on a longitudinal plane, okay, so what you require need or to calculate is first the shear force here acting on this plane. We have seen how to calculate the shear force in bending moment and shear force module. Okay, next is you need to have the location at which you want to calculate this shearing stresses. Okay, now the whatever is the area coming above this point where you want to calculate the shearing stresses, okay, above this point, that will be your A area. Y bar is the central distance of this area from the neutral axis, Y bar. Okay, I, moment of inertia of this entire beam section, cross section. B is the width of the beam. Okay, if you identify or calculate these things, you'll be able to get the value of shearing stresses. Okay, so what actually we did, derivation we have come across, but first thing, if I come from beginning, first is we want to know what is the shearing stress within the beams. So we are trying to determine what is the shearing stress on a plane like this here, longitudinal plane. Till now we are dealing with the shearing stresses which were acting on this cross section here. Okay, but right now I am interested in shearing stresses which are acting here. Why this came into picture? First thing, we took a case of non-uniform bending. Okay, so in a non-uniform bending, you have moments acting something like this: m on one side, m plus dm on the other face of the beam. Okay, under such a situation, you come across an unbalanced force Ft. Okay, so that tells you that there should be some force, okay, which is acting on the longitudinal section of the beam, also on the longitudinal plane within the beam also. Okay, so that is where the shearing stresses are coming in picture on the longitudinal section here. Okay, so on the beam or within the beam you have that shearing stresses on the longitudinal section also. So we need to calculate those shearing stresses here. Okay, so we are trying to find out what is the shearing stresses on this longitudinal plane which is here. Okay, so these are the shearing stresses which are acting on this longitudinal plane, on these planes. Till now we dealt with shearing stresses in this particular plane here. Okay, in this module we are dealing with longitudinal shearing stresses. So for that what we did, we took this non-uniform bending. So we concluded that there is an unbalanced force which is acting over here due to non-uniform bending, and this is balanced by these longitudinal shearing forces. Okay, so now I'm interested in knowing what is the expression that will tell me the magnitude of this shearing stresses. Okay, so for that, this is the section of a beam which is considered here, which is subjected to movements m and m plus dm on its two faces, left and right face. Okay, due to this, there will be bending stress distribution, something like this. Okay, and in this section, again, we went for taking a small element of depth dy, this small element. This is the small portion dx, what we are considered in the span of the beam. Okay, and this dx has been taken out. And what are the stresses which are there on left and right side face due to bending moment? So we have written the expression for that. Sigma PL m by I into y, sigma PR m plus dm by I into y on the left and right side face. Now, because of these bending stresses, what are the forces? So sigma BL into the area of this face, B into dy. So that will tell you what is EFL. And similarly, sigma BR into the area of this face. Okay. On both sides, the area of the face are same. Left face and right face, they are in the same area, B into dy. Okay. So that told us what are the forces which are acting on the left and right face of the section. Now, what is the net force? It will be equal to Fr minus Fl. On this small element, the net force acting will be dft, which is equal to Fr minus Fl. Okay. Now, if I want to know what is the total force which is acting on this part of the beam, okay, this which we have considered A dash, B, I just have to integrate this dft between the limits yb and yt. YB is the bottom edge of our section, YT is the top edge of our section, what we have considered. A dash, B dash. In that section, YB is the bottom edge, YT is the top edge. So that's why I'm integrating this DFT between YB and YT. Okay. So on integrating, what it tells you that the net force EFT is equal to dm by I into AY bar. This is the net force, what is acting on the A dash, B dash. Okay. Now this has to be balanced by a longitudinal force, which is arising due to the shearing stresses or the stresses acting on the longitudinal plane of the beam. So what is that? Okay, we have taken a small part of that beam dx. So here, if tau is the longitudinal stresses, intensity of longitudinal stresses, the force due to this will be tau into B into dx, this area, tau into this area, that is B into dx. So Ft has to be equal to F, or Ft has to be equal to this tau into B into dx. In turn, Ft was nothing but dm by I into Ay bar. Okay, or if I rearrange them, I'll get this expression for the shearing stresses here. Tau, which is equal to Fay bar upon Ib. Okay, so this is how we calculate the shearing stresses in a beam. Please go through these things one by one. Very basic concepts are linked in this: centroid, finding the net force. Okay, so through that we have arrived at these this particular formula of shearing stresses. Please tell me if you want me to repeat any part in this derivation. Just for an example, I told you, if it is a rectangular cross section, the position of neutral axis will be at the mid depth. Okay, over here, this is neutral axis. How you apply this shearing stress formula for this any beam or cross section? Okay, so if that is the case, and what we are interested is, now let us say you want to know what is the uh, shearing stress acting somewhere over here. Okay, let us say at this point. Now you want to know what is the shearing stress. acting at this line. Okay, say if it is at a distance y from your neutral axis, this is the distance y of that section from the neutral axis, and you are asking me what is the shearing stress at this point xx. So what I require, first thing is I have to find what is the shear force acting on this beam. Let us say this is a simply supported beam here. Okay, so this is the beam what you have, simply supported beam, and it is subjected to some loading. It may be concentrated load or uniformly varying load, distributed load, any type of loading it is subjected to this. Now you are asking me what this is the section. Okay, so at this point, what is the shearing force on the longitudinal plane? You want to know that. Okay, so for that, what you need to do is, first is you have to find out what is the shear force at this section 1 1. What is the shear force here? Okay, so shear force at this section 1 1 has to be determined. It may be having any UDL or anything, any type of loading. First thing is you have to find what is this shear force F on at this particular section. Next, what you have to do is you want the shearing stress to be calculated. You need the property of the section. What? Moment of inertia I of the section, width of the beam, okay, which will be there with us, width of the beam, this width, okay, so that has to be known to us. Then third thing is what is the point at which you need to determine the shearing stress. So this is the point where you want to find tau. Okay, here you want to find out what is the value of shearing stress tau at this point over here at this section. So that is there. Then what is the area? What is this area A? It is the area of this particular part of the beam. Above this section, all this will come in this area A. So you have to find the area A above this section. Whatever the area is there above that section, so that will come over here. Okay. So this will be the area A. Okay. Then y bar. What is this y bar? It is the distance of the centroid of this area. So if this is the area centroidal distance, centroid, say let us say centroid is over here. Then this will be your y bar from this point till the neutral axis y bar. So that is the y bar. Okay, area, this is the area what you will calculate. A and y bar has to be determined. So on substituting all these in this equation, you will get to know what is the y bar, this tau value, shearing stress acting at this point. Okay, so we'll be taking up these calculations in further part. Okay, till now we had bending stress calculation. Now what we are dealing with is shearing stresses on a longitudinal section. So we are going to calculate this particular stress. I hope you have understood the derivation. If not, go through these and make sure that you have a clear idea of what is the shearing stress we are dealing with and how to calculate those shearing stresses. Okay, so we'll stop at this point. You can put your attendance. If you have any doubts, you can ask. Just wait. Please leave your attendance. That is your USN. If lateral entries are there, if you have USN, put the USN or else your name.